Hello student, welcome to my channel Learn Physics. Today I will be discussing significant figures, arithmetic operations of significant figures, error, relative error, combination of error, and all the ncert and exemplar numerical of significant figure and errors. I have already uploaded the video of dimensional formula of physical quantities and the numerical related to principle of dimensional homogeneity and dimensional analysis. If you watch this uploaded video, your concept becomes more and more clear. I hope you will understand this video and this help you to score better in your upcoming exam class 11, main, NEET and advanced. Please like, share, comment on this. And if you are new, subscribe my channel to get the best result in this examination. Okay, now let's start. Now, first of all, significant figures. This is the certain digit plus one uncertain digit. Okay, one uncertain digit. Okay, so significant figures equal to number of certain digits plus one uncertain digits. Now, rule of selecting significant figures. Look at this. Number one, all non-zero digits are significant. Look at this. 2, 6, 2, 3, 5, 6. Look at this. Here all are non-zero digits. So here look at this. The number of significant figure 1, 2, 3, 4, 5. Okay, no problem. Now all the zeros between two non-zero digits are significant, no matter where the decimal point is at all. Look at this. Look at this 6.0025. Look at this. Here, this is the non-zero digits. This is the non-zero digits. These two zero within the non-zero digits. So these two zeros are significant. So here number of significant figure, this is the 5. Okay. Now, if the number is less than 1, that is the decimal number. That is the number having decimal point. The zeros on the right of the decimal point but to the left of the non-zero digits are not significant. Now look at this here 0.002308. Look at this here, these two zeros are right of the decimal point and this is the left of the non-zero digits. So look at this, these two zero are not significant. So look at this here, number of significant figure or significant digit is the 2308. So this is the okay. Now look at this, the terminal or trailing zeros in a number without decimal point are not significant. So look at this 1200. Look at this, these two zeros are trailing zero. So these are not significant. So look at this here, number of significant digit. This is the only 2. If unit is mentioned, so these two zeros are significant. If this is the 200 kilometer, so look at this, as unit is mentioned, so these two zeros are significant. So look at this here, number of significant digit is 4. Last, the trailing zeros in a number with decimal point are significant. Look at this 3.500. Look at this. This is the trailing zero. These are significant. So look at this here, number of significant digit. This is the 4. Now look at this 0.06900. These are the trailing zeros. So these are significant. So look at this here, number of significant digit. This is the 4. Okay, understood. Now next problem, The power of 10 are not significant. The power of 10 is not significant. Okay, not significant. Look at this, 6.023 into 10 to the power 23. Look at this is not significant. Look at this is not significant. So here number of significant figure is 6.023. So this is the 4. So it has 4 significant figure. No problem. If unit changes, the number of significant figure remains same. Look at this. Here 2.3 meter has 6 significant figure. Now, if it is converted into centimeter, it can be written as 12.3 into 10 to the power 2 centimeter. If it is converted to millimeter, it can be written as 2.3 into 10 to the power 3 millimeter. If it is converted to kilometer, so look at this becomes 0.00123. This is the kilometer. So look at this, in each case, the number of significant figure remains same. So in unit conversion, number of significant figure remains same. Okay, now some numerical from NCRT. Now look at this, NCRT 2.10. State the number of significant figures in the following. Look at this, 0.007. Look at this, the 0 between decimal point and non-zero digits are not significant. So look at this, here number of significant digit, this equal to 1. Now 2.64 into 10 to the power 24 kg. Look at this, the power of 10 are not significant. So look at this, here significant figure, this is the 3. Now look at this, 2.370 gram per cc. Look at this, for a decimal point, for a number having decimal point, the trailing zeros are significant. So look at this, here number of significant figure is 4. Okay. Now look at this, 6.320 joule. Look at this 0 is the trailing zero of a number having decimal point. So this 0 is significant. Therefore, look at this, here number of significant digit is 4. Now look at this, 6.032 Newton per meter square. Look at this is the 4 significant figure. Now look at this, 0.006032 meter square. So look at these zeros are between decimal point and non-zero digits. So these are not significant. So here number of significant digit, this is the 4. Okay, next. Now, rounding of the uncertain digit of a significant figure. Look at this, a number 2.746 is rounded up to 3 significant figure. So look at this, 2.746. This is rounded in 3 significant figure. So look at this, we take first of all 3 figures. So look at this is the 2.74. After 4, there is a 6 more than 5. So 1 is added here. So look at this, the number becomes 2.75. Okay, understood? Now look at this, another number 2.743 is rounded up to 3 significant figures. So look at this, here 2.74, and after 2.74 there is a 3. This is the less than 5. So no addition takes place. So approximate value of this is the 2.74, and look at this is the 2.75. Okay. Look at this, the rule by convention is that the preceding digit is raised by 1 if insignificant digit to be dropped is more than 5, and is left unchanged if the latter is less than 5. Now there is another rule. If the preceding digit is even and the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Now look at this. Suppose 2.745, 2.735, 2.765, 2.755. Look at this. If this number is converted into 3 digits number, so look at this. This is the 3 digits. Look at this. This is the 3 digits. This is the 3 digits. This is the 3 digits. So look at the before 5 there is an even number. So no addition takes place. This is the 2.74. Now look at this. Before 5 there is a odd number. So one addition takes place. So this also equals to 2.74. Now look at this. This is the now look at 3 digit number. Now before 5 there is an even number. So look at this. This is the 2.76. Now look at this. Before 5 there is also 5 odd number. So look at this. This is the 2.76 is the number. Okay, understood. Next. Now next, the rules of determining the uncertainty in the result of arithmetic calculation, that is addition, subtraction, division and multiplication. Okay. Now rules of arithmetic operations with significant figures. Okay. First of all, division and multiplication. Now look at this. In multiplication or division, the final result should retain as many as significant figures as there is in the original number with the least significant figures. Look at this. This figure has an 3 significant figure. This is an 4 significant figure. So significant figure of the result is the same as the original number having least significant figure. Now look at this. Suppose this is the 200 meter. Look at this. It has 4 significant figure. Look at this. This is the 10 kg. So look at this. It has 2 significant figure. So result has only 2 significant figure. So this can be written as 20 into 10 to the power 3 kg meter. Okay, understood. Next. Now question number 2. In addition or subtraction, the final result should retain as many as decimal places as there in the number with least decimal places. Okay, so look at this. The result should retain as many decimal places as are there in the number with least decimal places. Look at this. Suppose 2.3520 plus 1.235 plus 1.1. So look at this. It has 4 decimal places. It has 3 decimal places. It has 1 decimal places. So result have only 1 decimal places. Okay, understood? Now look at this here. Look at this here. This plus this plus this. Look at this. It has 2 decimal places. It has 1 decimal places. It has 3 decimal places. So result should have 1 decimal places. So look at this. This is the addition of this is 663.821. So look at this. If look at this, after 663.8, this is the 21. This is the less than 50. So no addition takes place. So this becomes 663.8. Okay, understood. Exemplar 2. The sum of the numbers this and this are appropriate significant figures. Look at this. It has 2 decimal places. It has 1 decimal places. It has 3 decimal places. So result should have 1 decimal places. So look at this. This is the 3 decimal places. This is the no decimal places. This is the 1 decimal places. This is correct. Okay. Now look at this. The mass and volume of a body is 4.237 gram and 2.5 cc respectively. The density of the material of the body. Look at this. This is the 4 significant figure. This is the 2 significant figure. So result have the significant figure as that of original number which has least significant, digit. So look at this, here two significant digit, so result has two significant digit. Look at this, so look at this, it has five significant digit, wrong. It has three significant, wrong. Look at this, it has two significant digit, so this is the correct. Okay, now look at this is the 2.5. The length and breadth of a rectangular sheet, this is the 6.3, this is the 16.2, and this is the 10.1 centimeter respectively. The area of the sheet appropriate significant figures. Okay, now look at this, it has three significant figure, it also has three significant figure, so result has three significant figure. Now look at this, it has three significant figure, so this is the correct. This is the five significant figure, this is incorrect. This is four, incorrect. This is five, incorrect. Okay, now look at this least count error. The smallest value that can be measured by a measuring instrument is called least count. Okay, look at this, a scale measured 1 millimeter. So least count of the meter scale is 0.1 centimeter. Normally, the least count of slide calipers, this is the 0.01 centimeter. The least count of screw gauge, this is the 0.001 centimeter. Okay, now the least count of normal clock is 1 second. Okay, the least count error is the error associated with the resolution of the instrument. For example, a vernier caliper has a least count 0.01 centimeter. Spherometer may have a least count 0.001 centimeter. Least count error belongs to the category of random error. Now error. Suppose measured value of a physical quantity be A1, A2, A3, AN. So average value of the measurement A equal to, this is the A1 plus F2 plus A3 plus this is the AN by N. So average of the measured value is called correct value. Understood? Now error in first measurement, this is the delta A1. This is the A1 minus A. Now delta A2, error in second measurement, this is the A2 minus A. Error of third measurement, this is the delta A3, this is the A3 minus A. So look at this, the absolute error delta A, this is the average value of this error. So look at this, the average value of error A1 minus A mod plus A2 minus A mod plus this is the N minus A mod whole divided by N. This is the absolute error. Now the physical quantity is written as, this is the A plus minus delta A. This is the this is the correct value and this is the error in measurement. Now look at this, delta A by A is called, this is the relative error. Okay, if relative error is expressed in percentage, it is called percentage error. So percentage error delta A by A into 100%. Okay, understood? Next. Now look at this example 2.7. We measure the period of oscillation of a simple pendulum. In successive measurement, the reading turned out to be 2.63, 2.56, 2.42, 2.71, 2.80. Now look at this, the significant figure or significant digit equal to reliable digit plus one uncertain digit. Look at this here, 6, 5, 4, 7, 8. So second digit is the unreliable. Therefore, look at this, we can write in a correct significant figure, we get the average value of period of oscillation. Look at this, t equal to, look at this is the 2.6 plus, this is the 2.6, look at this here 2.56, so this is the 2.6. Look at this, plus this is the 2.4, no problem. This is the 2.7. Look at this is the 2.7. Look at this is the 2.8. Divide by, this is the 5. Okay. Now look at this here, 2 plus, look at this, 0.6 plus 0.6, 1.2. 1.2 plus 0.4, 1.6. 1.6 plus 1.7. So look at this, 2.3. 2.3 plus, look at this, 8. So 3.1. So look at this, 3.1 divided by 5. So look at it, this is the 6. Therefore, 2.6 is the correct value of the period. Now look at this delta t. Look at this here, error in this measurement. Look at this, 2.6 minus 2.6. So this is the 0. Plus 2.6. Look at this, 2.6, 2.6. This also 0. Look at this, look at this is the 2.4 minus 2.6. So this is the minus 0.2. So this is the plus 0.2. Okay. Now 2.7 minus 2.6. So this is the 0.1. Now 2.8 minus 2.6. So look at this is the 0.2. Whole divide by, this is the 5. So this is the 0.1. Therefore, error. So look at this. T is the, this is the 2.6 plus minus 0.1 second. No problem. So look at this, 0.1 second is the absolute error. And relative error, look at this is the 0.1 by 2.6 is the relative error. This is the delta t by t. Now what is the percentage error? If relative error is expressed as percentage, it is called percentage error. So look at this is the 1 by 26 by 100. So this is the 4%. Okay, understood? Next, rule of addition. Suppose a equal to, this is the x plus y. So error of a is the arithmetic sum of error of x plus arithmetic plus y. Now error of b, if b equal to, this is the x minus y. So look at this, the error of b is the sum of arithmetic error of x and y. Now suppose c equal to, this is the sum constant k x to the power n. So look at this, in this case the relative error, this is the delta c by c, this equal to, this is the power, so power n into, this is the delta x by x. Now d is the multiplication, suppose k x into y. So here relative error of d is equal to relative error of x plus, this is the relative error of y. Now e equal to, look at this is the k, this is the x by y. K is the constant. So look at this here, relative error of e is equal to relative error of x plus, this is the relative error of y. Again, f equal to, this is the k x to the power m y to the power n by z to the power p. So look at this here, delta f by f. This equal to, look at this here, del m into delta x by x plus n into delta y by y plus p into delta z by z. And finally 1 by g equal to 1 by x plus 1 by y. Now this equal to, this is the delta z by g square equal to 1 delta x by x square plus delta y by y square. Okay, understood? Now I will be solving some numerical related to this. Okay. Now an example 2.8. The temperature of two bodies measured by a thermometer are 20 degrees Celsius plus minus 0.5 degrees Celsius and T2 equal to 50 degrees Celsius plus minus 0.5 degrees Celsius. Calculate the temperature difference and error therein. Now look at this for error. Now look at this. So difference of temperature, this is the delta T equal to this is the T2 minus T1. So look at this. This is the 50 plus minus 0.5 minus this is the 20 plus minus zero point 0.5. Now look at this. Here number is subtracted but error is always added. So look at this. This is the 30 plus minus. This is the zero point 0.5 plus zero point 0.5. So this is the 1. So error in measurement is 1 degree Celsius and difference is 30 degrees Celsius. Okay. Now look at this and numerical 2.9. The resistance are equal to V by I, where V is to 100 plus minus 5 volt, I equal to 10 plus minus zero point 0.2 ampere, find the percentage error in R. Now look at this. This is the R equal to V by I. Now we know the relative error of R is equal to the relative error of V plus this is the relative error of I. Okay, no problem. Now relative error of V, look at this. This is the 5 by 100. No problem. Plus, look at this. This is the, now look at this. This is the 0.2 by this is the 10. So here 5 by 100 plus 2 by 100. So look at this. This is the 7 by 100. So percentage error, this is multiplied by 100. So this is the 7%. So error in measurement of R, this is the 7%. Okay. Next. Now look at this. Example 2.10. The resistors of resistances R1 equal to 100 plus minus 3 ohm, R2 equal to 200 plus minus 4 ohm are connected in series. In parallel, find the equivalent resistance in series combination and parallel combination. Use the relation R equals to R1 plus R2 and this relation. Okay. Now look at this here. R equal to this is the R1 plus R2. Now what is R1? This is the 100 plus minus 3. This is the 100 plus minus 3. What is R2? This is the 200 plus minus 4. So look at this. This is the 300 plus minus 7 ohm. Okay, no problem. Now look at this. We have to calculate equivalent resistance in parallel combination. So look at this here. 1 by R dash. This equal to 1 by R. R1 plus 1 by R. Okay. Now look at this. This is the 1 by 100 plus 1 by 200. So look at this. This is the 3 by 200. So look at this. So R dash becomes, this is the 200 by 3. So look at this. This is the 66.7 ohm is the accurate value of resistance. Now we have to calculate error. Look at this. This is the delta R dash by R dash square. This equal to delta R1 by R1 square. This is the delta R2 by R2 square. Okay. So look at this delta R dash by R dash square. Delta R dash. This equal to, look at this. This is the R dash by R1 whole square into delta R1. Because R dash, because this equation is multiplied by the term, this is the R dash square. Plus, look at this. This is the, look at this. This is the R dash by this is the R2 whole square into delta R. Okay. Now look at this. This is the delta R dash. This equals to R dash by R1. Look at this. R dash is the 200 by 3. R1 is the 100. So R dash by R1 is the 2 by 3 whole square into this is the 3. Plus, look at this. R dash is the 203. 200 by 3. R2 is the 200. So this is the 1 by 3 whole square into 4. So we get, look at this. This is the 4 by 9 into 3. So 12 by 9. 12 by 9 plus 4 by 9. So look at this. This is the 16 by 9. So look at this. This is the 1.8. So R dash equal to, this is the 66.7 plus minus 1.8. Okay, understood. Next, look at this. Example 2.12. The period of oscillation of a simple pendulum T equals to 2 pi root under L by G. The measured value of L is 20.0 centimeter known to 1 millimeter accuracy, and time for 100 oscillation of the pendulum is found to be 90 seconds using a wristwatch of 1 second resolution. What is the accuracy in measurement in determination of G? Now look at this. Here total time is T. So T equal to, this is the 90 second. Now delta T equal to, this is the 1 second because its resolution is 1 second. Now look at this L, this equal to, this is the 20.0 centimeter, and delta L, this equals to, this is the 0.1 centimeter. Okay. Now time period T equal to, this is the T by, this is the oscillation, number of oscillation is the 100. Now time period T equal to, this is the 2 pi root under L by G. So look at this, this is the T square equal to 4 pi square, this is the L by G. So look at this, G equal to, this is the 4 pi square, this is the L by T square. Okay. Now look at this, here delta Z by G, this equals to, this is the delta L by L plus 2 delta T by T. Now look at this here, delta T by T equal to, this is the delta small t by T. Now delta T equal to, this is the 0, this is the 1 second at T 90 seconds. So this is the 1 by 9. Now put the value. So this is the 0.1 by, this is the 20.0 plus 2 into, this is the 1 by 9. So look at this is the 1 by 200 plus, this is the 2 by, this is the 9. Okay. Now to find the percentage error, delta G by G equal to, this is the 1 by 200 into 100% plus, this is the 2 by 90 into 100%. So look at this is the 0.5% plus, look at this, 200 by 90. So look at this is the 2.4%. So finally we get 2.9%. That is almost 3%. Okay.